Okay, moving on to the calculate part now. I have sort of copy and pasted my free body diagrams from the analyze and represent part because they are useful, and we are going to use them to help us build our, help us work through the calculate part. So I've copy and pasted them here, maybe not qualitatively accurate, but the content is the same. The first part of the calculate part is principles. What are the most important concepts, laws, definitions that we might need to solve this problem? Because I'm solving this with forces, I am definitely going to want my law of motion, F net is equal to the mass times the acceleration. I will definitely use that. And because I am interested in the final speed of the blocks, probably going to need some kinematics. So I'm going to use this equation, Vf squared is equal to V initial squared plus 2a times delta h. So this is a kinematics equation which relates my final velocity, my final speed, I should say, to the initial speed plus 2 times the acceleration times delta h, however much the objects have moved. So in this case, I'm going to, actually I'll come back to that in a little bit. We'll rewrite that when we need it. So here's my principles, and now we're going to move on to finding a symbolic expression of our Vf, our final speed here. So to do this, I'm going to write down my law of motion for both blocks. I'm going to start with m1. So I'm just going to label this here, m1. Starting with m1, I don't really need to worry too much about the vertical direction because the block is not moving up or down. I already know that my normal force is equal to my gravitational force here. I'm only concerned with the horizontal motion. So I'm going to write my tension on 1 by the rope is equal to m1 times a. Okie doke. Good, that looks good. Our tension force and our acceleration is going in the same direction, so they've got the same sign. Let's do m2. Now we don't need to worry about the horizontal direction. m2 is moving vertically up and down. I've called the downwards direction to be positive, so I'm going to start with my gravitational force minus my tension force, because my tension force is going in the opposite direction, minus my tension force on 2 by the rope is equal to m2 times a. A is in the same direction as the gravitational force, so these two should have the same sign. Okay, so the other nice thing about this situation, because I'm working with an ideal pulley and an ideal string, I can write down that Ft, the tension force on 1 by the rope, is equal to the tension force on 2 by the rope. And this lets me directly plug this equation into this equation using through that tension force. So that's what I'm going to do next. Now I'm going to be using this mass 2. I'm going to rewrite my gravitational force now as m2 times g minus m1 times a. I plugged in that value for the tension force because I know that those are equal. This is equal to m2 times a. All right. Now all I need to do is rearrange and solve for a. I'm looking for the acceleration, right? That's what I have here in my kinematics equation. So I'm going to rearrange and solve for a. I'm going to rewrite this as a is equal to, I've got m2 times g up top. I add that over, factor the a out, and divide by the sum of the masses, m1 plus m2. So there's our acceleration. And now I'm going to use my kinematics equation and sort of rewrite it a little bit. So to start, I'm just going to write Vf squared is equal to V initial squared plus 2a. And then now I'm going to replace delta h with L because I know L is how far the blocks have moved. And I know that this thing, the initial velocity, is 0. That's coming from my assumption. All right, so now I'm ready to plug in for a. And I get a final symbolic expression. So I'm going to leave this as Vf squared for now. So Vf squared is equal to 2 times a. So this whole thing. So we've got 2 times, up top we've got m2g. We also have this L, so I'm going to multiply that there, divided by m1 plus m2. All right. So there is our final symbolic expression for the square of the final speed. To find the final speed, we can take the square root, and we'll do that at the end. But to simplify things for the moment, so I don't have to carry around a square root, I will leave it this way. So there's our final symbolic expression. All right, we have a symbolic expression. I know the masses, right? I know M1, I know M2, I know G, and I know L. So we have fully defined this value, the final speed, in terms of things that we know. Now I need to plug numbers in. So I'm going to plug numbers in here. VF squared is equal to, I have 2 here. The mass 2 was 1 kilogram. Remember to always carry around your units when you're plugging numbers in. It's really important and can be very helpful. Multiplied by G, which I'm going to estimate as 10 meters per second squared. And then L is 0.75 meters. Went off the screen a little bit there. I won't go past that. Divide this by, we've got 1 kilogram plus 4 kilograms. That was the mass of block 1. All right, so now let's just keep going here. Let's solve for this. So VF squared is equal to, I've got 2 times 10 is 20. We're dividing by this kilogram here, so I know that that unit is going to go away. So I've got something like 20 over 5. This becomes, units are meters per second squared. And I'm multiplying by 0.75 meters. I'm going to rewrite this as 3/4 meter. So it's a little bit easier on our math. Right, so then we get our final speed squared. 20 over 5 is 4. That will cancel that, and we're left with 3. So we have 3 meters squared, second squared. So this tells me that my final speed is the square root of 3 meters per second. All right, so I'm fully done with my calculate part. I have figured out what my principles are, I've determined my final symbolic expression, and I have come up with my final numeric expression. Let's move on to sense making.